Let knowledge flow like a river without any hindrance. Don't make it like a stagnant pool. Structural design only. A channel with different vision. Shear force and bending moment analysis of a beam under different load and support condition. An introduction of mu diagram part 1.
Hello everyone, I am P.S. Strategy with you. Today I am going to explain you how we can calculate the bending moment and shear force of a beam under different load and support conditions in Excel by mu diagram. This is part 1, and in this part you are going to watch for the point load. I hope you are going to enjoy this video. Minimum requirement IS 456-2000 SP16, Excel software 2010 onward. Before start of the lecture, please like, share and subscribe my channel.
Basic criteria for the calculation. Load CG for a point load is the point of the application. Load CG of U.D.L is the midpoint of the load length. For other load, we have to calculate the CG from its geometry. The maximum moment is the moment under simply supported condition. For FEM or fixed end moment, this span moment we have to distribute. By considering moment from opposite support, we have to calculate the support reaction. Analysis of a simply supported beam when point load at center. This is the picture of a simply supported beam with point load at center. Left hand support A, right hand support B, midpoint C. Total length L. RA is the reaction of left hand support and RB the reaction of right hand support. Bending pattern of a simply supported beam when point load at center. For simply supported beam, point load at center, it will try to bend in this manner. Shear force diagram of the beam. Number 1, reaction on left hand support and right hand support is equal to RA is equal to RB is equal to P by 2. Shear force at left hand support is equal to VA and right hand support is equal to VB is equal to P by 2. Shear force at right of the midspan is equal to VA minus P. That means after crossing this point, we'll get this shear force and the value is minus P by 2. And this is our shear force diagram. RA is equal to P by 2, RB is equal to P by 2 and here it is P by 2. Bending moment diagram of the beam. When point load is at center and beam is simply supported. We know for simply supported beam, moment at support, that is MA is equal to 0 and MB is equal to 0. RA is equal to P by 2, RB is equal to P by 2. And moment at C, that is center, is MC is equal to RA into L by 2 is equal to P into L by 4. Analysis of a fixed beam when point load at center. This is the pictorial view of fixed beam. Support A and B both are fixed and point load P at the center. RA reaction of left hand side and RB reaction of right hand side. Bending pattern of fixed beam with point load at center, this type. Here it will be hogging type, here also hogging, and at the center it will be sagging type. Mu diagram for simply supported beam load at center. Mu diagram is nothing but the area under the bending moment curve. This is our bending moment curve, and this red portion is the area under the BM curve. So mu is equal to half into L into MC. MC is the height of a triangle. So L by 2 into
P into L by 4 is equal to P into L square by 8. It is the area. Mean dot diagram for the fixed beam point load at center. Similarly, mean dot diagram is nothing but the diagram of bending moment, area of the bending moment,
extent moment curve. Here MA is equal to MB. We know that. So it will be a
triangular type area. So mu dot is equal to L into MA or MB, you can write that. And this is our superimposed mu diagram for point load.
for fixed end moment and
This hatched area is common for both fixed end moment and span moment. And this span moment would be equal to MC minus MA. Return support is equal to MA.
is equal to right hand support, that is MB, and say span moment at C is equal to MC. Mu C is equal to mu C into L by 2. We also know MC is equal to minus PL by 8. Mu is equal to minus PL square by 8. Mu dot is equal to MA into L. We also know that mu plus mu dot is equal to 0 or minus mu dot is equal to mu. Therefore, minus MA into L is equal to minus PL square by 8. Finally, fixed end moment of MA is equal to MB is equal to P into L by 8. Span moment of the fixed beam, say it is FC. Sorry. Say it is MFC. MFC is the algebraic sum of MC and MA, and from its geometry, span moment will be maximum at L by 2 distance. Therefore, MFC is equal to minus PL by 4 plus PL by 8. Maximum span moment MFC of the fixed beam is equal to minus P into L by 8. Now, bending moment diagram for the fixed beam when point load at center
is equal to P into L by 8. MFC is equal to P minus PL into L by 8, and MB is equal to PL by 8.
shear force for the fixed beam. Reaction at left hand support is equal to right hand support. We know that. Say left hand support reaction is equal to R1 and right hand support reaction is equal to R2. Taking moment about B, that is this point, about this point we have RA into L, length of the beam, plus MA, that is this moment, minus P, this load, P into L by 2 minus MB is equal to 0. We know MA is equal to MB. Therefore, R1 into L is equal to P into L by 2, or R1 is equal to P by 2. So,
then shear force on left hand support is equal to BA and right hand support DB. And at the center, it is BC. So, it's equal to R1 is equal to R2 is equal to P by 2. And this is our shear force diagram. Left hand support BA is equal to P by 2, BC is equal to minus P by 2, DB is equal to P by 2. Deflection of the fixed beam at C with point load at center. Deflection of the fixed end beam. Beam at any section at a distance x from A is equal to MA. Is equal to mu x minus mu dot A. Mx is equal to P into x by 2 minus P into L by 8. Second, we know Mx is equal to E into I into d2y dx2. It is a differential equation of bending moment at any section, where E is the elastic modulus, I moment of inertia. So we can write EI d2y dx2 is equal to Px by 2 minus PL by 8. By integrating this equation, we have EI dy dx is
x Px squared by 4 minus P into L into x by 8 plus C1. C1, the integration constant, and we know when x is equal to 0, dy dx is equal to 0. Therefore, C1 is equal to 0. So, the equation will be EI dy dx plus P into x squared by 4 minus P into L into x by 8. This is the equation for the slope of the beam at any section, and by integrating this, EIY is equal to P into x cube divided by 12 minus P into Lx square by 16. We know that the maximum deflection occurs at the center C or at L.
So, EIYC is equal to P into L by 2 cube by 12 minus P into L into L by 2 square by 16 is equal to PL cube by 96 minus PL cube by 64. So we equal to PL cube by 192. Now we know EI into YC is equal to minus P into L cube by 192. Finally, deflection at center of the fixed beam with a point load at center YC is equal to minus P into L cube by 192 into EI. Negative sign for downward deflection.
Analysis of a simply supported beam with point load away from center. This is a picture. Simply supported beam, point load away from center. Here, our load is towards A, not at the center. Once again, reaction at A is equal to RA and reaction at B is equal to RB. Total length L and length of the left hand support to load is A and load to right hand support is B. Bending pattern of the beam will be like this curve. At P, the deflection will be maximum. Reaction and span moment of the beam. Reaction on left hand support RA is equal to P into B by L. Reaction on right hand support is equal to RB is equal to P into A by L. Span moment at C is equal to MC is equal to RA into A is equal to minus P into B into A by L. Shear force of the beam. Say shear force at A is equal to VA is equal to RA, and shear force at B is equal to VB is equal to RB. VA is equal to P into B by L, and VB is equal to P into A by L. Shear force at C is equal to VC is equal to VA minus P. VC is equal to P into B by L minus P is equal to minus P into L minus B by L is equal to minus P into A by L, because we know L is equal to A plus B. By substituting the value of L by A plus B, we have P into A by L. Shear force diagram of the beam. This is our VA is equal to P into B by 2. This is our VC is equal to P into A by 2 with the sign negative. VB is equal to P into A by 2. This is our bending moment diagram. Here bending moment at left side support is equal to 0, and that of right hand support it is also 0. At C we have minus P into A into B by L. Fixed beam with point load away from the center. Once again, this is RA and this is RB. This side is A, this side is B, and this position is C. This is the length A, this is length B. Bending pattern of a fixed beam with point load away from center will be like that. This is hogging type, and this is also hogging type, and this is sagging type. Maximum deflection we are going to find at C. Fixed end moment when point load away from the center. Simply support a span moment at C. MC is equal to P into A into B by L. This moment will be distributed in the ratio of A and B. Fixed end moment at support. Fixed end moment at supports. Say FEM at A is equal to MA and FEM at B is equal to MB. MA is equal to P into A into B by L, that is simply supported moment, into B by L, this is the ratio, equal to M into A into B square by L square. Similarly, MB is equal to P. Similarly, MB is equal to P into A into B by L. This is simply supported moment at SC, that is MC, into B by L ratio is equal to P into A square into B by L square. Fixed end moment by mu diagram when point load away from the center. Mu diagram for simply supported beam when point load away from the center is like that. And we know mu diagram is nothing but the area under the bending moment curve. Here it is a triangle and the height is equal to MC is equal to P into A into B by L. So mu is equal to half into L, that is base, into P into A into B by L is equal to P into A into B by 2. This 2L will be nullified. Bending moment diagram for fixed beam. Here it is MA and it is MB. So area will be half into MA plus MB into L. And this is superimposing of mu diagram for span moment. This is MA, this is MB, and this is MS or MC. And this is MFS. It is fixed end condition. The span moment will be MFS. Now we know mu plus mu dot is equal to 0, or mu dot is equal to minus mu. Then half MA plus MB into L is equal to minus P into A into B by 2, or MA plus B is equal to minus P into A into B by L. This is our equation number 1. By taking moment of mu diagram about A, we have to split the triangle into two right angle triangle. Area AA is equal to A by 2 into P into A into B by L is equal to P square B by 2L, and CG, distance from A, is equal to x1 is equal to 2 into A by 3. Then IA, that is first portion of the triangle, is A into x1, that is equal to P into A square into B by 2L into 2 by 3, 2 into A by 3 is equal to P into A into B by 6 into L into 2 into A square. So area of the second part of this triangle is AB. So AB is equal to P into A into B by L into B by 2, as CG distance from A is equal to x2 is equal to A plus B by 3. Moment of inertia of this A2 is equal to IB is equal to AB into x2 is equal to P into A into B by 2L into B into A plus B by 3 within bracket is equal to P into A into B by 2L into thrice AB plus B square by 3. Now we know I2 is equal to IA plus IB. I2 is equal to this expression, P into A into B by 6 into L within bracket 2 into A square plus 3 into A into B plus B square. This is our equation number 2. Area under the curve of fixed end moment mu dot is equal to L into M plus MB divided by 2, and CG distance from A is equal to x3 is equal to 1/3 L into MA plus 2MB by MA plus MB. Moment of inertia of A3 about A is equal to I3. I3 is equal to A3 into X3 is equal to L into MA plus MB by 2 into L into MA plus 2MB by 3 into MA plus MB is equal to MA plus 2MB by 6 into L square. This is our equation number 3. Now we know I3 plus I2 is equal to 0. Therefore I3 is equal to minus I2. By equating 2 and 3 we have MA plus 2MB by 6 into L square is equal to minus P into A into B by 6L into 2 S square plus thrice AB plus B square within bracket. MA plus, therefore we can write MA plus 2MB is equal to minus P into A into B by L cube into 2 S square plus 3A into B plus B square. And this is our equation number 4. By subtracting the equation 1 from 4, we have MA plus 2MB minus MA minus MB is equal to P into A into B by L minus P into A into B by L cube into within bracket 2 into A square plus 3AB plus B square. Therefore MB is equal to P into A into B by L into within second bracket 1 minus 1 by L square into within first bracket 2 into A square plus thrice AB plus B square, second bracket close. MB is equal to P into A into B by L into 1 minus 1 by L square plus 2A square plus 2AB plus AB plus B square. Thrice AB is equal to 2AB plus AB. MB is equal to P into A into B by L into 1 minus 1 by L square into 2 into A. I'm taking the common 2A from this 2. So A plus B plus, I'm taking common B from this 2, A plus B. That is, we have MB is equal to P into A into B by L into 1 minus 1 by L square into A plus B into 2A plus B. Again we know L is equal to A plus B. Therefore MB is equal to 1 minus 1 by L square into L. This is L plus 2A plus B is equal to P into A into B by L into 1 minus 1 by L into A plus B plus A. 2A is equal to A plus A. MB is equal to P into A into B by L into 1 by L into within second bracket L minus A plus B minus A is equal to P into A into B by L square into within first bracket L minus A is equal to minus P into A square into B by L square. Once again we know MA plus MB is equal to minus P into A into B by L. MA is equal to minus P into A into B by L minus MB is equal to P into A square into B by L square minus P into AB by L. Therefore MA is equal to P into A into B by L square into A minus L is equal to P into A minus P into A into B by L square into minus B is equal to minus PA B square by L square. Finally we have MA is equal to P into A into B square by L square, or MB is equal to P into A square into B by L square with a sign negative. Calculation of span moment of a fixed beam when point load away from center. Span moment of the fixed beam at C. Hogging moment at C. Say hogging moment at C is equal to MC1. APM at A and B is equal to M and B. Rate of change of moment of fixed end moment MA minus MB by L. L is equal to beam length. MC1 is equal to MA plus A into MB minus MA by L, where A is the distance of load from left hand side. Simply suppose its sagging moment at C is equal to MC is equal to minus P into A into B into L. Finally, span moment, say span moment MS is equal to MC1 plus MC, algebraic sum. Bending moment diagram of fixed beam with point load away from center. Here it is P into A into B square by L square. Here it is minus P into A square B L square. And here it is MA minus A into MA plus MA minus MB minus PA into B by L. Deflection at the point of application of the load of a fixed end beam with point load away from the center. At any section of a beam at a distance x from A, mx is equal to mu x minus mu dot x. Mu x is equal to P into B into x by L minus MA minus MB minus MA into x by L. Mx is equal to EI d2y dx2. E elastic modulus and I moment of inertia. EI d2y dx2 is equal to PBx by L minus MA minus MB minus MA into x by L, or EI d2y dx2 is equal to P into B into x by L minus P into A into B square by L square minus within bracket P square B by L square minus P AB square by L square into x by L, or EI d2y dx2 is equal to P into B into x by L minus P into A into B square by L square minus P A B into A minus B by x into x by L cube. This is our equation number 1. By integrating the above equation number 1, we have ER dy dx is equal to PBx square by 2L minus P into A into B square into x by L square minus P into A into B within bracket A minus B into x square by 2 into L cube plus C1. C1 is equal to integration constant, and we know that when x is equal to 0, dy dx is equal to 0, therefore C1 is equal to 0. Then we can write EI dy dx is equal to P into Bx square divided by 2L minus P into A into B into A minus B into x square by 2L cube minus A into B square into x by L square, or EI dy dx is equal to P into B into x square by 2L into 1 minus A into A minus B by L square minus P A B square into x by L square, or EI dy dx is equal to P into B into x square by 2L into within bracket L square minus S square plus AB by L square minus P into A into B square into x by L square. Therefore, again we know L is equal to A plus B. Therefore, EI dy dx is equal to P into B into x square by 2L into A plus B whole square minus A square plus AB by L square minus PAB square into x by L square, or DEI dy dx is equal to PBX square by 2L into A square plus B square plus 2AB minus A square plus A into B by L square minus P into A into B square into X by L square. Or EI dy dx is equal to P into B square into X square into 3 into A plus B by 2 into L cube minus P into A into B square into X square by S square is equal to P into B square into X square into within bracket 3A plus B by 2L cube minus P into A into B square into X by L square. By integrating the above equation, we have EIY is equal to P B square into X cube plus CA plus B by 6L cube minus PAB square X square by 2L square plus C1. Sorry, it should be C2, and C2 integral constant, and when x is equal to 0, y is equal to 0, C2 is equal to 0. We have to consider this is C2. By mistake, I have written here C1. Therefore, EI is y is equal to P into B square into x cube into 3 plus 3 into A plus B within bracket by 6 L cube minus P into AB square into x square by 2L square, or EIY is equal to P into B square into x square y 6 into L cube into x into 3A plus B minus 3A into L. This is our equation number 2. Now, at the point of maximum deflection, dy dx is equal to 0. By differentiating the above equation, we have EI dy dx is equal to thrice pb square into x square into 3a in 3 into a plus b by 6l cube minus 2 pa b square into x by 2l square l square. Now, by substituting dy dx is equal to 0, we have x into 3a plus b by 12 is equal to a, or x is equal to 2 into a into l divided by thrice a plus b. By substituting the value of x to equation number 1, we have EIY pb square into x square by 6l cube into x into 3 into a plus b within bracket minus 3 into a into l, and x is equal to 2al 3a plus b. The EIY max, that is at C, P into B square by 6L cube into 3A plus B into X cube minus 3A into L into X square. Thrice EIY max is equal to P B square by 6L cube into 8A cube into L cube into thrice A plus B divided by thrice A plus B whole cube minus PB square by 6L cube into 12 A cube into L cube divided by thrice A plus B whole square, or EIY max is equal to 8P A cube B square by 6 into thrice A plus this B whole square minus 12 into P into A cube into B square divided by 6 into thrice A plus B whole square is equal to minus 2/3 P into A cube into B square by thrice A plus B whole square, or Y max is equal to minus 2 into 3 EI by P into A cube into B square divided by A plus B whole square. Negative sign indicating downward deflection. The deflection under the load can be found by substituting x is equal to A in equation 2. EIY is equal to P B square A square by 6L cube into A into 3A plus B minus 3AL, or EIY is equal to P B square X square by 6L cube into X into 3A plus B minus 3 thrice AL, or EIY is equal to P into B square into A square by 6L cube into A into A thrice A plus B minus thrice A into A plus B, or EIY is equal to P into B square into A square by 6L cube into thrice A square plus AB minus thrice A square minus thrice AB, or EIY is equal to P into B square into A square by 6L cube minus 2 into A into B is equal to minus P into B cube A cube y thrice L cube, or y is equal to minus P B cube A cube by thrice EI whole cube. Finally, deflection at C of the fixed end beam with point load A from the center, YC is equal to minus P A cube into B by thrice L cube into EI. That is this formula, and negative sign indicating downward deflection. Now I am switching over to the Excel spreadsheet for the numerical calculation. Welcome to my Excel spreadsheet for the design and analysis of beam under different load and support condition, part 1. Look here, beam length 6 meter and beam width 250 mm, depth 500. Say our load case is dead load case. We can also change this dead load, live load, etc. And it is a point load. Point load. Now look here. Point load P is equal to 10 kilonewton, and this is 0. This is W2, not required here. Now we have to put the value of A. Say I am considering 2 meter from left hand support. 2 meter. Now it is okay. This two switch is now inoperative. It will be reactivate after the completion of this P shoot. And look here, fixed end beam moment, left hand support 8.89 and right hand support minus 4.44 kilonewton and span 5.93 kilonewton meter. Maximum shear force, left hand support 7.41, right hand support 2.59. Reaction for simply supported condition. Left hand support 6.67, right hand support 3.33 kilonewton, span moment 13.33 kilonewton. Deflection, this is fixed end condition 1.3 to 1.36, and L by D ratio 44,219, and it's okay. Now I am changing the load position. Say it is in the middle. Look here, fixed end beam moment, left hand support 7.5, right hand support 7.5, right hand support 7.5, and span moment 7.5. Maximum shear force 5, left hand support and right hand support 5. Deflection 1.1598 and L by D ratio of 5176. Now I am changing this load to right hand side towards B. So I am changing A is equal to 4. And here, look here, for simply supported condition, left hand support reaction 3.33 kilonewton, right hand support 6.67, span moment 13.33 kilonewton, fixed beam moment, left hand support 4.44 kilonewton meter, right hand support 8.89 kilonewton meter, span moment 5.93 kilonewton meter. Maximum shear force at support, left hand support 2.59, right hand support 7.41.
Further, I have to say that don't change the value with rate covered. It is auto-generated. If you change the rate covered value, it may be corrupted. Further, here is some point, clear cover. You can change the clear cover. We can change the FCK, that is characteristic strength of concrete, characteristic strength of steel, etc. We can change easily from drop down menu.
Yes, you are the right person to me, whom I can request. Don't worry, I am not asking any money from you. Since you are watching this video till now, yes, you are the connoisseur of the structural design and analysis. I have a request to you. I am asking more organic watching hour from you. Only you have the veto power to add the organic watching hour to my channel. You may think, how can you do this? You can do this by taking the following action. By providing more time in my channel, by sharing the link of my channel, by making regular comment and providing like, by any measure that you know but I don't know. I can assure you that your investment will provide you the dividend in near future. End of bending moment and shear force of a beam under different load and support condition in Excel part of 1. I hope you enjoyed it. Please don't forget to subscribe my channel. Thank you.